So this is the last lecture of our course, and we are going to discuss here the most advanced and modern subject in modern theoretical physics. We're going to discuss homogeneous space-times, which solve Einstein equation with lambda not zero, cosmological constant, non-zero cosmological constant, but with, for the case when matter energy momentum tensor is zero, and we're going to discuss only the ground state solutions of Einstein equation with non-zero cosmological constant, so-called vacuum solutions of Einstein equation in this case, or well, they are homogeneous spaces. We will see what happens. So actually the case with when we have lambda equal to this, Einstein equations basically look as follows: r mu nu minus half of g mu nu r equal to half lambda g mu nu. And this case, well, up to this factor half, this case actually can be mimicked by the case when which we have been considering in the previous lecture. There we have been considering T mu nu of the form rho rho times u mu u nu plus p times u mu u nu minus g mu nu. And if p is equal minus rho, which corresponds to the case of omega equals to minus 1, this an equation, such a peculiar equation of state, then one can see that energy momentum tensor in this case is reduced to the case rho times g mu nu, which is exactly this case if rho is constant. For the case of rho constant, we encounter exactly this case. And in fact, rho constant agrees, for this case of energy momentum tensor, rho constant agrees with Einstein equation of motion and energy conservation. So we are going to discuss the following situation when g mu nu, which is Einstein tensor, this guy, is equal to plus minus d minus 1 times d minus 2 over 2 times h squared g mu nu, where mu and nu run from 0 to d minus 1. So we're going to consider d-dimensional, from 0 to d minus 1 is d-dimensional spaces of constant curvature, space-times of constant curvature. Here h is Hubble constant. Hubble constant. In this actually case, it is actually a constant because here h is independent of anything, and this lambda here is related to this h as follows. It's lambda equal to d minus 1 times d minus 2 over 2 h squared, and plus sign corresponds to the positive curvature, while minus sign here corresponds to negative. So this is de Sitter space, this is anti de Sitter space. Anyway, why it is positive curvature and why it is negative, this case is negative curvature, will become clear in a moment when we'll dig into details of this space. So let me start my consideration with a de Sitter space, with a positive curvature. Well, there are, of course, one can do the same way as we did in the previous lecture, using this energy momentum tensor, etc., etc. But for many reasons, I prefer another way. Instead of using matter energy momentum tensor of this form with rho equals to constant, I prefer to address another way. such that geometric properties of the spaces that we're discussing become obvious, apparent. So, for example, de Sitter space, I am going to explain this, but let me first make the statement. De Sitter space can be expressed as the following hypersurface. This is a metric tensor, Minkowskian metric tensor, in d+1 dimensional spacetime. So d-dimensional de Sitter spacetime can be embedded into d+1 dimensional spacetime. So this is a metric in that d+1 dimensional spacetime. Anyways, this I'm going to explain in a moment. So this is Minkowskian tensor in d+1 dimension. So the equation which is written here is just x0 squared plus x1 squared plus etc. plus xd squared. And, well, this is by definition. And hypersurface equation for the hypersurface is as follows. It's just h to the minus 2, the same h as here. So this hyperboloid is embedded into the Minkowskian space-time, d+1 dimensional Minkowskian space-time, with this metric. So we're going to explain why this is, in fact, space of constant curvature, or homogeneous space. Well, there are several ways to see that. Well, first way is the following. It's so-called Wick rotation. That if we make a change of x0 to I x d+1, both here and here, we obtain that minus sign here is changed to the plus sign here under this change, and this is changed to delta A B, well, with a minus sign. Well, that doesn't matter because we can omit this sign. It is not relevant for anything. So we obtain d+1 dimensional Euclidean space and d-dimensional sphere embedded into this space. So what we obtain is just space of, obviously, space of constant curvature of the radius 1 over h, which is apparent from this equation, and which does solve this equation in Euclidean signature. So we can define Einstein's theory in the same manner in space of Euclidean symmetry. Nowhere in the derivation of this equation we have used the fact that this metric is Minkowskian, of Minkowskian signature. So the same procedures are applicable in Euclidean signature. We can obtain the same equation. And the sphere will solve this equation with plus sign here. And during this change, Wick rotation, the curvature of the spacetime is not changed. That's the reason de Sitter space is called the spacetime of positive constant curvature. And that is a way to see that it is in fact the space of constant curvature. That's the first way of seeing that. The second way of seeing this is as follows. One can see that isometry of this space contains the following group, SO d minus 1, 1, which is nothing but the Lorentzian rotations of this, Lorentzian boosts and rotations of this spacetime. This group doesn't change this equation. So this group of Lorentzian rotations of this spacetime is the isometric group of the de Sitter spacetime, so which is apparent from the equation. At the same time, an arbitrary point, say for example the point x0, x1, and so forth, xd, well x2, let me write x2 also for obvious reasons, etc. For this point, which is 0, 1 over h 0, and etc. 0 everywhere, this point belongs to this hyperboloid. It is moved under this group, but remains unchanged under the action of the SO. I should say that, well, actually, I'm sorry to say that this is, the isometry group is actually SOD1 without D minus, and the subgroup of this, which doesn't change this point, is actually SOD minus 1, SOD minus 1, comma 1. So because here D x's and 1 with minus sign x0. That's the reason SOD is isometry of this. And the stabilizer, so-called stabilizer, the subgroup of this group which doesn't move arbitrary point of this space-time, say this one, is of this form. Then one can see that this space that we are discussing is homogeneous space, SOD, comma 1 over SOD minus 1, comma 1. This is a compare actually this with SOD plus 1 over SOD for the sphere. You see under this Wick rotation, we change this to this and this to this. So in fact all of this homogeneous space is transformed into this. And we obtain, so what we see from these considerations. This is a second way of seeing the fact that our space is of constant curvature, homogeneous space. The fact that it is homogeneous space of this form tells us that every point of this space is equivalent to every other, because it can be obtained by the action of this group. And every direction from every point of this space is equivalent to every other, up to the difference between space-like and time-like directions. So I explained two ways without calculation to see that we are dealing with a space of constant curvature.